be here. And yeah, I'm going to talk about the colourful Helly theorem. And I should say this is joint work with Leonardo Martinez Sandoval and Nathan Rubin, who are both in Israel, in the Ben Gurion University in Beersheba. So let me start with Helly's theorem. So Helly's theorem is one of the most important theorems in discrete geometry. It says that if you have a family of convex sets, usually a finite family or some extra condition is needed, such that every d+1 elements of this family have a point in common, then all of the elements in the family have a point in common. So this is the picture you should think about. So you have a bunch of convex sets. This is in the plane. So I want every 3 to intersect. And essentially what the theorem is saying is that this cannot happen, right? This is a fourth convex set that intersects every other 2. But it's avoiding the middle part. This is impossible. If this happens, then it also has to contain a point in this intersection. So I want to talk about how you can generalize this theorem. And one thing you can do is think about flats. So a flat is just an affine subspace of Rd. So in the plane, a flat can be a line if it's a one flat or a point, or the whole plane. This would be a 2 flat of the plane, but it's kind of trivial because it's the whole thing. Also, you can think what happens if not all of the d+1 tuples intersect. And another way that has been used is to find a colorful version of the theorem, which I will talk more about in a second. But these are the 3 things I want to talk about. So what about flats? So imagine that you have a family of convex sets in Rd, and every n of them have a k transversal. A k transversal here is just a k-dimensional flat that is intersecting all of these n elements. Then all of the elements should have a k transversal. This kind of generalizes Helly because Helly talks about a 0 transversal, which is a point. And then you conclude that this has a 0 transversal to the whole family. Now the problem with this is that this is false. And there are very easy examples. So in the plane you can think of this configuration of circles. So every 3 of them, for every 3 of them you can find a line. So if I take the top 3, I have this horizontal line, and this line crosses all of them. So this is a 1 transversal to this 3 tuple. And I can do the same for any triple, but I cannot find a line through all of them, right? You can try. And well, that tells you that this is false for n equal 3.
How about having transversal which intersects the interior of convex set?
Yeah, you can make these a little bit bigger, and then you still don't have a transversal to all of them. And you can try this with n equals 4, and then you find another counterexample, which is this one. Here you have a transversal to any 4 of them, but you don't have a transversal to the whole family. And you can keep on finding examples in the plane. So, but this is sometimes true, right? This is true when k is 0. So in some special cases this might be true, but in general, no. But there is something that has been done. So if you're talking about things of codimension 1, so d-1 transversals, these are just hyperplanes, then you cannot guarantee that there is something intersecting everything, but you can find a bounded number, a small number of hyperplanes that do intersect the whole thing. Right? So here, now you don't have one element that intersects everything. You have some relatively small family of hyperplanes that intersect the whole thing. So here it's important that this number of hyperplanes does not depend on the family F. It doesn't depend on how many elements the family has. It only depends on the dimension. So I think for dimension 2, it's known that you can do this with 4 lines, and in higher dimensions, well, the number gets a little bit bigger, but it always depends only on the dimension and not on the family. And well, you have this theorem for hyperplanes.
What
n, this n.
So this h of d depends on n.
H of d doesn't depend on n, it depends on the dimension. Which n?
If every n elements. So it's d plus 1.
Yeah. This was for, sorry. This theorem holds when you're taking d plus 1 tuples. So when you're taking transversals to d plus 1 tuples of your family. If you make n smaller, then you have no hope of having anything. And if you make it bigger, then you have, in particular, this. So like it starts working from d plus 1. And in general, there is nothing similar for the rest of the flats. So there are some examples for lines where in high dimensions where this is not working. And well, this is all I want to say about transversals, but transversals is a really interesting topic. It's one that I like a lot. So just because I say that there is not much done, don't dislike it. It's one of my favorite research topics. So this is what I want to say about Helly for flats. So essentially no theorem, but remember this one. There is something where there's some constant depending only on the dimension. So the second thing was, what if not all of the d plus 1 tuples intersect? Now, there is a very nice theorem here, which is called the fractional Helly theorem. And what this says is that essentially if not all of the d plus 1 tuples intersect, but some fraction of them intersect, then I cannot conclude that the whole family has a point in common, but I can conclude that many of them have a point in common. So here, for every alpha I choose here, I know that there's going to exist some positive proportion of them where I can still find a point in common, which is kind of what you would expect, right? If many d plus 1 tuples have a point in common, then there should be a point in common to many of the elements of the family. So this theorem, the first time I heard about it was when I heard about this Hadwiger and de Brunner's PQ problem, which was proved by Allon and Kleitman. And I have this. So the PQ problem says the following. Imagine that you have a family of convex sets, and this time you don't know that every certain number of them have a point in common, but you know that every time you take Q of the elements of the family, P of them have a point in common. So like the first interesting example is when Q is 4 and P is 3. Then this says that whenever you take 4 convex sets in the plane, 3 of them have a point in common. Then what you can conclude is that there is a number P that depends only on PQ and the dimension. There is a number P and a family of P points which together intersect the whole family F. So this was an open problem for a while, and then Allon and Kleitman gave a solution, and their solution is really nice, but it's also really complicated. At least it was for me when I saw it the first time. And it uses...
Is that why it's called notorious?
Yes, for me at least. This is my opinion. And it uses 2 ingredients. One is using this fractional Helly, and the other one is considering weak epsilon nets, which I don't want to talk about, so I'll just skip it. So this is the fractional Helly theorem. And lastly, I want to talk about colourful Helly. So colourful Helly is a very strange theorem. At least I haven't gotten around it completely yet. So it says that, imagine that you have your family of convex sets, but this time it comes with colors. So you can express F as a union of d plus 1 sets, and each one of these represents a color. So F1 is the first color, and you think that the elements here are colored with the color 1, and so on. So here are everything that's colored with the color d plus 1. So imagine that you have this, And now your hypothesis changes a bit. Now you want every heterochromatic subset of d plus 1 elements of F to have a point in common. That is, you want to take one element from each color, exactly one element from each color, and you want that for every choice you find a point in their intersection. Then what you can conclude is that for some color you have a point common to all of its elements. So somehow you're talking about things that involve all of the colors, and you conclude something about one of the colors. So this is the colourful Helly theorem, and this is what my talk is going to be about. So I want to show you how you can prove this theorem, and I'm going to show you, I hope my computer doesn't start making sounds. I'm going to show you a proof by Lovas, which I think wasn't published, by him at least. So in the proof you start with a random direction. I'll say why it has to be random later. And then for every two elements, I'm going to do the proof in the plane, but this, you can do it in any dimension. So for every d colors, so I have d plus 1 colors, but for every d colors I can choose one element of each color and consider their intersection, which is non-empty. And for each one of those I can choose the rightmost point. So for example, here I have a red and a blue convex set, and they intersect in some region, and I choose the rightmost point. Here I have a green and a blue, and I choose the rightmost point. And I do this for every pair, or d-tuple in general, that are of different colors. And now I take the leftmost point of these, of the ones I chose. And I'm going to show that this point is in every element of one of the color classes. Which color? Well, this point is determined by a blue and a red. So the missing color there is green. I'm going to show that this point is in all of the greens. And for that, I'm going to take a vertical line through this point and consider the semi-space that's to the right. Now here, it's important that this point is unique. And that's why I can't choose any direction. But for most directions, this will happen. So I'm going to show you that all of the greens are here, and to do that I'm going to use the usual Helly theorem. So I have four sets here. I have a gray set, a green set, a red, and a blue. So if I show that every three of these intersect, by Helly's theorem I can conclude that they all intersect, right? So let me do that. Of course the red, blue, and gray intersect because this is how I constructed them. The red, green, and gray intersect because I know that the red and green intersect at some point, and I know that it's the rightmost intersection point of these two sets has to be to the right of this point. Otherwise, this wouldn't be the leftmost point. So this means it has to be on the gray region. So those three intersect. The blue, green, and gray is the same thing. And which one am I missing? That's all of them, right? So every three of these intersect. Therefore, they all have to intersect. But they have to intersect in this point because this is the only point of intersection between the blue, the red, and the gray. So this means that any green set has to be here, has to intersect this point. So this point is in all of the greens. So this is a nice proof, and you can see that this hypothesis of having these intersections is really strong, right? So it feels like there should be something more. So what else could we do? So this is an example of in dimension 2. I'm going to have red sets, which are vertical line segments, blue sets, which are horizontal, and the last color is going to be this green one, and it's just going to be a big thing. And here I have only 3 and 3, but imagine I have many in each direction. many segments in both directions. Then of course because any two lines with different directions have to intersect, then every red and every blue have to intersect, and they have to intersect in the green part because the green part is pretty big. So here every colorful triple intersects, but I cannot say much about the rest of the colors, right? Because any point intersects at most one blue and one red. So I need at least as many points as I have red lines, right? And this, of course, you can do it in higher dimensions with hyperplanes. Any D hyperplanes intersect, and here there's a color missing, but imagine that there's another color that's some very big. I mean, you just take the whole RD as your last color. And I write here very colorful Helly because there is an analog of Helly's theorem, which is called the Kara-Teodori theorem. And they're in some sense duals of each other. And there's a colorful Helly, there's a colorful Kara-Teodori. And there's a very colorful Kara-Teodori, which was in part proved by Andreas here and many other people at the same time. And the conclusion of this very colorful Kara-Teodori is that you can say something about two of the colors. Unfortunately, that doesn't work here. You cannot say that there is a second color that has a point in common, which is a bit annoying. But you can see, I'm going to silence my phone. I think it's my phone. And I don't know why. It's really late in Mexico. So, yeah. So notice here that in both cases, with one line, I can cross all of the colors, which is, I mean, this is generally how you think of the sets in colorful Helly. At least this is how I thought of them. So can we do anything in this direction? So there is a very easy trick you can do. So you know by colorful Helly that there is one color that has a point in common. So get rid of it. Forget about it and consider only D colors. You can project all the convex sets of these D remaining colors to some hyperplane. And there you still have the same intersections. So in this hyperplane, you need one color less to have this colorful Helly hypothesis. So you can conclude in the hyperplane that there is a point in common to all of them. And this point lifts to a line. So by projecting, you can find a line that intersects all of the elements of one color. Right? So, for example, if I projected this in I projected down. So then all of these red segments would turn into points, and these would be the whole thing. So I can find a point in common to all of the blues, and when I take it back to R2, this turns into a vertical line. So here I can conclude that there is a vertical line transversal to all of the blues. And here I can choose any direction. So for any direction, I can find a line that intersects all of the elements of one of the colors. And once I did that, I can project once again and find a plane that intersects an element of all of a third color, all of the elements of a third color, and I can do this for every dimension. But this is somehow not so good because I'm only talking about one color at a time, and here it seems that with one line I should be able to intersect everything. So why? So this is just the colorful Helly again. So I can find a color with a point transversal, but we managed to do a little bit more. So we can find another family, which is not the same one as this one, that can be pierced with few points, or if this is not the case, then the whole family can be crossed with few lines. which doesn't follow from this fact. And from this fact, for every direction you find a line that crosses all of the elements of one color, but maybe it's the same color for all of the directions. And then you don't say anything about the rest of the colors. So this one is saying that you can find a small set of lines that cross absolutely everything. Of course, you cannot, sometimes you cannot say this. And an example is when there are two families that are very big. So the first family take the whole plane several times for the first family. The second family take the same thing, many planes at the same time. And for the third family, you can choose just points scattered around. Then I can find a point to the first family, I can find a point to the second family. I cannot find anything for the third. But having a point to the second family, this is what we wanted for this very colorful heli. So sometimes we can get it, and if not, then the family has to be really special so that we can cross it with a small number of lines. So let me restate this. Here I don't really care about this first color, right? And this is just colorful heli, so I'll get rid of it from the beginning. And here is the same statement, only that without this last color. So if I have D colors in RD, then I can find some elements which can be pierced by a small number of points, or I can cross everything with a small number of lines. So can I do it with one line? And this actually took a while. The answer is no, and this is an example. Let me start with a triangle, and I'm going to construct the first family in the following way. I'm going to take I want to take triangles that have one vertex in each of the sides of this big triangle, and I want no three of them to intersect. So the way to do this is just start with any triangle at the beginning. It's better if you choose it like these two very close to this vertex and this one close to one of these two. And then choose a second one. Really doesn't matter as long as this side and this side don't intersect. And for the third one, you want to avoid this middle region. So you can choose it below this region, and then choose a point here that's to the right of this one, and then you can do this again. So you want it to be below this region, so you just take this line further below and move this point over here, and you can do this forever. So you can find the family. Now I want the family to be finite, so at some point I'll stop. But I can find an arbitrarily large family of triangles here so that no three of them intersect. And for the second family, this is in the plane. I'm going to take these segments, which are the sides of the triangle except some small neighborhood of the vertices. I have to choose this neighborhood small enough so that all of these sets intersect all of these sets. So these two satisfy the hypothesis, but you're going to say, okay, the red needs many points to be pierced, because each point can pierce only two of them at a time. So I need at least half as many points as elements I have. But the blue one I can pierce with 3 lines, with 3 points. So to avoid this, I'm going to take copies of these, very close, parallel to these segments, a little bit closer. So I can do this without any problems. And now this one needs many points because they're disjoint. It's still satisfying this hypothesis. So I cannot pierce everything with a small number of points. I can do it arbitrarily large. And I cannot do it with one line. So I can cross. So I need at least 2 lines to be able to cross everything. So the red sets, I can cross them with one line. And the blue sets, I cannot cross the 3 of them with one line. So a way to do it is like with a horizontal line here and a vertical line through the middle. And this crosses everything. But you cannot do it with one line. This is because of the blue sets. So we have a lower bound here, that is at least 2. And in general, we can do this in RD. So here we're going to need at least d over 2 lines. This is actually d plus 1 over 2 ceiling, but it's roughly d over 2 lines. And the way to construct it is you take a simplex. Let me do it in R3 because I can actually draw it. And then I'm going to take in this side triangles like the ones I just showed you. And then I'm going to do the cone from this opposite vertex. So imagine I draw many of them here. I'm only going to draw one. And then I take this other side and I do the same thing. So I have many smaller tetrahedra here. And then I'm going to remove some neighborhood of these two vertices. And I need to do that because otherwise all of the blues would have a point in common at that vertex. And all of the greens would have a point in common on this vertex. And then last, so this is 2 colors in R3, so I need an extra color. So for the last color, I'm going to take the triangles of this tetrahedron. Now, this would not be so good because I have one line through this vertex and the opposite face. So I have to remove a small neighborhood of the one-dimensional edges of the tetrahedron from each one of these faces, so that doesn't happen. But I can take a very small neighborhood and just take a smaller triangle of the third color in each of the faces of the tetrahedron. And this will satisfy the colorful hypothesis because, if I take a blue and a green, they look like this essentially. And if I take a side of the tetrahedron, then I can see here a point of intersection in the interior. Here as well. This point here is on the upper back face, and this point here is in the lower back face. So whenever I take one of each color, they intersect.
Don't all the blue intersect?
No, where?
How many blue are there?
As many as you want.
But aren't they all suspended down to...
Yeah, but I removed, look, here I had this point, but then I removed it. Yeah, you have to remove a small neighborhood here.
But are you saying that if you took 2 blue guys, their only intersection was...
No. Two blue guys can intersect, but 3 blue guys don't intersect. It's the same. So the blues look like this, like the red ones here.
But then you're suspending them down to some...
Yeah, so I have a point here, and I'm suspending...
So you're saying that that's the only point in common to 3?
Yeah. Yeah, which other point? If it had a point a little bit over here, then it would be in some plane that looks like this. Right? It's kind of... Yeah, it's a scaled copy. So the only intersection of 3 is this point, and that's why I have to remove it. Yeah. Right. So this example is good so far, and to pierce with a line all of the sides of a tetrahedron, of the interior of the sides, I need at least, I forget how many. So each line intersects 2. So I need 2 lines. Right? To intersect all 4 of them. And this can be generalized, and it's not so obvious how to do it, but you start with a simplex and you take triangles made of consecutive vertices. So if I label the vertices from 0 to d, then for each number between 1 and d minus 1, I'll take this triangle. So 3 consecutive vertices in this ordering. And in that triangle, I'm going to take the same triangle example I had before. And then I'm not going to take the suspension. So I take every other vertex and add it to the triangle, and then take the convex hull at the end. And then, of course, I have to take care of things like removing things so that I remove silly intersections. So in the end, you have to remove a small neighborhood of of the d minus 2 skeleton of the simplex. And this only gives you d minus 1 colors. And the last color is going to be the facets of the simplex. And again, I have to be careful and I have to remove stuff so that I don't have trivial transversals. But this is not too complicated. You have to do it carefully. And there is a little bit of, like, you have to do some cases to show that the colorful hypothesis is being satisfied. But you can do this example and you find that you need ceiling of d plus 1 over 2 lines for everything. So there is some lower bound. But the upper bound is the interesting one, now that we know that this is not a trivial thing. So we have an improvement of this theorem for which I have no examples. So something that is stronger. So again, we have d plus 1 colors, and we have this colorful Helly hypothesis. So every time I take an heterochromatic family, they have to intersect at a point. And then I can reorder them somehow and find a number k such that these two things happen at the same time. So the union of the first k families, k colors, can be pierced with some small number of points. And here the and is important. Before it was an or, here it's an and. The rest of the elements can be crossed with a small number of k-dimensional flats. So I know this is a bit like hard to grasp at the first reading, so let's see what happens when you get k equal to 1. So when k is 1, this says that the first family can be pierced with few points, which we kind of knew because this is just the colorful Helly. And the rest of the elements can be crossed with few lines. Right? So this is one of the conclusions of the theorem I just showed you. So before I showed you that you have a point, and then either you have a point to something else, or you have lines to everything. So this is the case, lines to everything. And if k is at least 2, then you have few points to the whole thing. So this is the other case. And you have something extra. Right? You have that the rest of the elements can be crossed. Well, when it's exactly 2, it says that it can be crossed with few planes. And of course, it can be that you have a bigger k, which would be better because it tells you that you have more families that can be pierced with few points. So this is an improvement on the previous theorem. And we have no idea how these numbers are behaving in reality. So we only have upper bounds. And they're really bad upper bounds. So let me tell you something about how this is proved. So first we start with a very easy lemma. So imagine that now you have two colors, and I'm going to call them A and B. So I have two families of convex sets in some d-dimensional space. And we have this colorful hypothesis that every time I take one from each, I have non-empty intersection. Then either I can find a common point to all of the elements of A, or B can be crossed with few hyperplanes. And the proof of this is really easy. So imagine that you are not in the first case. So this is empty. Then you can find d plus 1 elements which are not intersecting, right? This is Helly. And if they are not intersecting, then I can find hyperplanes which look like this. So for each of these d plus 1 elements of A, I can find a hyperplane which is limiting a half space that contains it. That contains this one. So this line contains this one in one of its sides. And the same this one, this line with this set. And these semi-spaces don't have a point in common. So they look like this. They leave a simplex out. Now take any d of these hyperplanes. And imagine I take, I want to show that these d intersect all of the elements of B. So imagine that there is an element that doesn't touch any of these lines, of these hyperplanes. Then it has to be contained in one of the cells, right? But it has to be contained in the one in the one that's common to all of these half spaces, because it has to intersect every red one, every element of A. But that means it doesn't intersect this one, right? So these D hyperplanes were enough to intersect all of the elements of B. So this is kind of like a mini version of our main theorem, right? But now you only have two colors, and you're going all the way down to hyperplanes instead of looking for lines, planes, etc. And this is the first step of the proof. Now, at some point in the proof, we're going to need a fractional version of this. And also, this is not really the lemma we want. The lemma we want is a bit more complicated. So I'm just going to state it, but it's a bit technical. So you have two families of convex sets such that the intersections can be crossed by a small number of K flats. Now I know this looks a bit ugly, but I'll explain more in a second. And then you can conclude that either you can pierce the first one with few points, or you can cross the second one with few K-1 dimensional flats. And what we did before is the case when K equals D. So the fact that all of these intersections can be crossed by a D flat, well, a D flat is the whole space. So if you can cross it with the whole space, it just means that every one of these intersections is non-empty. And so this is the lemma we want. And to prove our theorem, what we have to do is use this lemma D minus 1 times. So we know from colourful heli that I have a point to one of the families. Now I want a point to a second family. So either I can find I can find a point, and if I cannot find a point, then a small number of points. If I cannot find a small number of points, then I'm in this case, and then I start iterating. So I just work on these flats in each one, and then I use this lemma, and again and again and again. So this is the heart of the proof. Now, the proof of this lemma is really complicated, and it follows the idea of Alon and Kleitman's proof of the PQ theorem. So instead of using weak epsilon nets, we use weak epsilon nets for hyperplanes, which is something that this is Alon and who?
Helly.
And Helly. Yes. So they did that. So we use epsilon nets for hyperplanes instead of their epsilon nets, and instead of the fractional heli, we use the fractional version of this one, and we kind of use the same tricks, the same ideas, and it just sort of follows through. And at the end, we get this nice theorem that I just showed you. But it's at least for me, it's the ideas of Alon and Kleitman are really good. So it's not something, I don't think it's an easy proof, but luckily we had Alon and Kleitman to follow.
I have a question. So you have maybe upper bound of a function f and g.
Yes. We have an upper bound. It's a really bad upper bound. Actually, we don't know how big it is asymptotically. I guess you could do it, but like each time we apply the lemma again, we have to iterate on the previous value we had. So it starts getting huge. And we have good bounds for these when, well, not for these, but for the original ones. For these, when we're talking about very small numbers, like when k is 1, and when D is small, then it's okay. But in general, it's horrible. One question is to find nicer numbers here. And so we have a conjecture. So imagine, again, that we have D colors, and we have the colorful Helly hypothesis. Then
Only D family system.
huh?
Only D family system.
Only D. So now I'm forgetting about the D plus 1 family. Then there should be numbers ki that add up to D, one for each color, such that every fi is crossed by a small number of ki flats, of flats of dimension ki. So what is this saying? So let's see what happens in the plane. So in the plane, you only have two colors. So you only have two k's, and they have to add up to 2. So the only possibilities are 0, 2, 1, 1, or 2, 0. So the 0, 2 is points to the first family, and planes to the second one, which is nothing, right? So it's only points to the first family. The 1, 1 is lines to the first and lines to the second, and the 0, 1 is the 2, 0 is planes to the first, which means nothing, and points to the second. So this we know does happen. So for D equals 2, it holds. Right? Having lines is the lemma I showed you, and having points is having points is just colorful Helly. If you go up to dimension 3, then you have more possibilities. So now you are going to have 3 colors, and they have to add up to 3. So you can have like 3, 0, 0, which would be points to 2 families, or what else? Or 2, 1, 0, which would be points to one, lines to another, and planes to another. And essentially that's it. Oh, and 1, 1, 1, which would be lines to everything. And up to permutations, that's it. So we think something like this should hold. So I think this is a nice problem. Probably and we don't know. What we have is, if you write it like this, you have this sum being much bigger than D. So we don't have counterexamples for this. Maybe it's interesting to find a counterexample, or a proof might be better. So okay, now this is all. Thank you.